So work. Work. Work is a scalar. You know what? Underline that. That's going to be hugely important, because what that's going to mean is this just became way, way, way easier. How do I add two vectors together? Draw them and then get triggy with it. How do I add scalars? I just add them. No trig. No nothing. It's defined. It's defined as the product of the force component in the direction of motion and this distance moved. It's defined as force times distance, but the force and the distance have to be in the same direction. The force and the distance have to be in the same direction. If the force and the distance aren't in the same direction, no work is being done. Now, we have a tendency, Clay, to get confused because work also is an English word. Most of us, when we hear the word work, we think tiredness. I'm doing work, I'm getting tired. No. In physics, you're only doing work if you are exerting a force on an object and that object is moving in the same direction, a distance, as the force. It's given by force times distance. What are the units? Well, the units could be a Newton meter, because that's what force times distance is, but we give this a special name. What do I measure work in? Joules. Symbol capital J, named after a scientist whose last name was Joule. Example 1 asks, how much work do you do when you lift, underline the word lift, a 35 kilogram mass to a height of 1.5 meters? Okay. Work equals force times distance. When you lift something, which force are you doing work against? So really you can think about this as Fg times distance. Oh, except, you gonna make it, Vikas? That's a long blink. It's okay. What is Fg? If I break that down even further, what have we been writing it as typically in the last unit? 2 letters. Mg. Mg. And you know what? We often call a height h. You can put a d there, but what we've really just done is we've just derived what last year you called gravitational potential energy. There. mgh. Now, before I go further, what's the force in this question? Looking for a word that begins with the letter G and rhymes with avity. Okay, gravity. When you lift something vertical, is gravity vertical? Are the force and the distance in the same direction? You are doing work. It's going to be 35 times 9.8 times 1.5. $514. You know what? I'll go to 3 sig figs. 515. 515 what? Work. Joules. 35 kilograms. That's about 80 pounds, maybe a bit more. Would it be tough to lift 80 pounds, a height of 1.5 meters? Well, you could, most of you do it, but it wouldn't be, you wouldn't want to do it like 30 times in a row. So 515 joules, it's a little tiring. You know what? Actually, it's not tiring. It all depends on how fast you're doing the work. If you gave me 3 hours to do that, say you built a little hill that I could gently push it up, piece of cake. If you gave me 2 seconds to do that, or 1 second to do that, or a half second to do that, I'm going to be getting tired. Okay, so now I got to figure out how to stop this thing. I've gone to a new, yes I can. How much work does a hiker do on a 50 kilogram backpack if he carries it to the top of a 750 meter mountain? Well, Work equals force times distance. Here's the other beauty about work. Did you remember, what did I ask you to underline near the top of the page because I said it was really important? Work is a scalar. Don't write this down. Even if the mountain looks like this, we don't care that the hiker followed this path. When you're climbing a mountain, which force are you doing work against? So since gravity is in this direction, all I care about is the distance in that direction, the height. I don't care about the path that I took to get there. What that's going to mean is work and energy are going to be very useful tools for analyzing irregular, curvy surfaces, like roller coasters. If you want to calculate how much work this person did, you know what? It's going to be, again, gravity times the height, force times distance, mgh. Where the backpack is 50 kilograms, it's a pretty heavy backpack. 50 kilograms, about 120 pounds, so a small person. G, 9.8. So, could you piggyback someone up a 750 meter high mountain? You could. Wouldn't be pleasant, especially if you do it quickly. How many joules of energy is that? 50 times 9.8 times 750, 367,500. I'm going to go 3.68 times 10 to the 1, 2, 3, 4, 5th. Joules. We're going to be pulling out a lot more scientific notation because the numbers get big fast. A ball on the end of a rope is following a circular path because of a constant force exerted on the ball, like this. I can feel that there's a force exerted on the ball because I can feel the ball tugging my hand, and forces come in pairs. There is tension in the string. How much work am I doing on the ball right now? None. Why? Because the direction of the force is towards the center of the circle. That's what the question says. But the distance is most definitely not towards the center of the circle. So this is a trick question. The force is this way. The distance is that way. No work. In general, a force in the same direction as the motion, like F1 in the picture below, does positive work, or if you want to phrase it differently, makes the object gain energy. A force opposite to motion, like F2 below, does negative work, or makes the object lose energy. So you can have negative work, but it's not a direction because it's a scalar, it's a quantity. If you have negative work, you've lost energy. It's not giving you any kind of a direction indication. It's just that you get less than you had before. Positive work, you've gained energy. Okay? What if the force is at an angle? Like example 4. Did I say angle? What's the first word that pops into our mind? Components. So a child is pulling a wagon along the driveway. You know what? I'm going to make this a little bit bigger. So here's the wagon. And it looks like we're pulling with a force F. And an angle theta. We would break this into components Fy and Fx. Hey, this is almost good review for your test next class. Which force is in the same direction that the wagon is going to move? F, Fy, or Fx? Max. So really, work equals Fx times distance. that okay, Kyle? But let's get an expression for fx. Let's see. If this is theta here, F, the force that we know, opposite, adjacent, or hypotenuse. What about Fx? Which trig function? I think I also have this. Cosine of theta adjacent over hypotenuse. Is that okay, Spence?
Yeah.
Let's get the Fx by itself. How would I get the Fx? So you know what? I'm going to go like this on the same line. And what I'm going to say now, because is apparently I can plug that into there. This is really the work equation. It's force times distance cosine of theta. Kai was going to put his phone away before I lovingly freak out. Thank you. Let's see how well this works. If this is straight that way, what's theta? If there's no angle, what's theta? As a number, 0 degrees. So, hey, what is the cosine of 0 degrees? Try that on your calculator. What? And you get force times distance, the equation that we used last year all the time. What about Josh and his piggyback? What was the angle between gravity and the direction of motion when Josh was piggybacking Vikas? How big was that angle? What's the cosine of 90? I wonder if it's 0. That would be kind of cool. Is it? And that means the work done is 0. Ah. Oh, what about, I'll come back to you in a second. What about this example here? What if the force is this way? Sorry, the distance is this way, and the force is this way. How many degrees is this? Hey, what's the cosine of 180? -1? Oh, there's my negative work. So actually, if you take physics next year, you'll probably be given this as your generic force equation, and we'll just clue in, Travis, you know what? If you're in the same direction, theta is 0, cosine of 0 is 1, and it vanishes. If you're in opposite direction, theta is 180 degrees, cosine of 180 degrees is -1, you get negative work. Oh, if they're 90 degrees to each other, no work, otherwise take a component. Oh, no, there, I've got the component in the actual equation. I've done that already. Now, I've talked about that, but did we do components this past unit quite a bit? Yeah? And did we do components in Unit 1 kinematics quite a bit? You know what? I'm not going to give you components in this unit. I've flogged you enough. I might in the homework, but your tests are going to be the force and the distances are almost always 99% of the time going to be in a nice straight line. Question, Josh?
If there's friction, then I would be doing that.
If there was friction, you would be losing some energy to friction because friction would be that way if you were walking that way.
Yeah, so that's better friction.
Well, but then we see really then what your question. First of all, I would say if you weren't walking, if you were dragging instead, that would be easier to deal with. The fact that you're walking, the example that I gave, okay, let me pause the video for a second because I do need to clarify this. First of all, let's make this big again, Mr. Duke. What we avoided last year, Mitchell, is, hey, what if the force is not constant? What if it's a changing force? And this is the one we're going to be using an awful lot this year. I like this, I like this, I like this, I like this. This is important. It turns out, Clay, that work is also the area under a force versus distance graph. So here's an example. What's on the y-axis, Kevin?
Distance.
On the y-axis, Kevin. What's on the x-axis? We call this a force versus distance graph. And I want you to notice the force is getting bigger, which means it's not a constant force. I can't go force times distance. However, it turns out the amount of work done will be the area underneath this graph. So this question asks, how much work is done moving this object from 2 meters to 6 meters? Well, it's going to be that area. What shape is that? Begins with the letter T. Yep, someone said it quietly. It's not a triangle, sorry. It does begin with a TR. In German, sorry, what's the English word? Trapezoid. Trapezoid. A trapezoid has two parallel sides, there, and two sides that aren't parallel. Anybody know the equation, the formula for the area of a trapezoid? There is one. No, it's not on your formula sheet, Manny. Don't look. Oh, I got to pause. You go. Hang on. There is a formula for the area of a trapezoid. The only issue is it's redundant because of what Kyle hinted at. If all of you do this, every trapezoid can be broken up into what two shapes? A triangle and a rectangle. And you know what? Those ones we know. Okay? So although there is a formula for the area of a trapezoid, I'll get you straight there. In terms of time savings and having to memorize or know an obscure formula, meh. You know what? I'm going to call this area 1. I'm going to call this area 2. And I'm going to say, you know what? The work is going to be area 1 plus area 2. The work is going to be, what shape is area 1? What is the area of a triangle? That is, put your phone away, Clay. Folks, stay off the phones, please. That is on your formula sheet. It's base times height divided by 2, or 1/2 the base times the height. And what's the area of a rectangle? Is that one on your formula sheet? I doubt it. This one they probably expect you to know. What's the area of a rectangle? Length times width, or you can call it base times height. So, how much work did we do moving this object from 2 meters to 6 meters? How long is the base of triangle area 1? 4? What's the height of triangle area 1? Careful, don't say 3. From here to here. 1, yes? Divided by 2 plus, let's look at the rectangle. What's the length of the rectangle? Also 4. What's the width of the rectangle? I think that's supposed to be 2 if I could draw properly, yes? In fact, I think it's 4 times 2, 8 plus 4 divided by 2. Isn't it 8 plus 2? I think the answer is 10, yeah? I'll go 10.0, so I go to 3 sig figs. And it's work units. This we're going to be using more and more often, Alex, the notion that the area of a force versus distance graph, especially if the force is changing, that's also how much work was done. That lets us get away from force times distance. Well, that lets us deal with changing forces. Energy. Energy is the ability to do work. If an object has energy, it has the ability to exert a force over a distance. And there are many, 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 many forms of energy. There's the energy of motion. Remember what we called a moving object and how much energy it had last year? Kinetic energy. Another type of energy is heat, created by which force creates a lot of heat? Friction. We're going to pretend that all heat comes from friction, just to keep the math simple. Gravitational potential energy. So again, chemical potential energy. This is energy that's stored in chemicals. Gunpowder, the food you eat is a great example of chemical stored potential energy. That's why you eat food. You need to get your energy from somewhere. Other forms, sound energy, that's a form of energy. Elastic energy, the energy stored in a rubber band. Nuclear energy, the energy stored in the nucleus of an atom. Many, many, many different types of energy. we're going to be looking at two primary types and then occasionally heat. Yes?
You said that the direction matters for work, right?
Yep.
So, could you explain it to me where, so you're lifting an object with a crane.
Yep.
Okay, you got the cable coming along, comes into the drum, and then the swing motor operates the drum. What's actually doing the work? Would it be the swing motor, even though it wouldn't be in the same direction?
As soon as you start moving in a circle, we're going to be looking at centripetal circular force, and you're going to find the rules change. There's also, the fancy word is angular force, if you take physics next year. There's also going to be a whole new series of equations for angular or centripetal kinetic energy. And there's going to be a whole new series of equations for angular momentum. So my temporary answer to you right now is, since we're moving in a circle, I can't give you a good explanation. I can say this: yes, the cable is doing the work, but if you want to calculate how much work the cable is doing, work is being done on the cable by the drum, which is moving in a circle. If you want to calculate just how much work the drum is doing, then we would need to use circular kinetic energy and some of the circular equations. And I'll be honest, I've forgotten them. I'd have to derive them. I know they're there, and I think I could derive them if you gave me about a half an hour, but I'd be doing it uncertainly. I'd have to go back to first principles and work it out. Okay? What we would say is this: the short answer is the crane motor is doing the work in lifting the object if you ignore all the intermediate pieces. That I can say, whatever energy the object gained by gaining in height, that amount of energy was lost by the crane motor. Now, of course, it's plugged in to something, so it's getting the energy reimbursed, or it's got a gasoline motor. The energy is still coming from somewhere anyways.
Would you be able to eventually calculate what the diesel motor would be producing, power all the hydraulics and everything?
Yeah, but you said power. See, now we're talking about a different concept. Now we're talking about wattage, and yes, and we will. Okay. The two most common types of energy we're going to look at. Here's the first type. Sometimes when we do work, we make things move. The energy of motion. Fill in the proof below to find an expression for motion energy. Now, I should pause for a second here. Technically, the symbol for energy on your formula sheet is that. The problem is, in a couple of units, this is going to be electric field. This is going to be energy, and it's going to get confusing. So I do something that's wrong. I use two capital letters. That's my abbreviation for kinetic energy. That's my abbreviation for potential energy. That is wrong. You should never, using two capital letters, that should be two different variables. That should be something called P times something called E. I'm going to break a rule just to avoid confusion. By the way, really what we should do, if you take physics next year, you'll find the symbol for energy is a capital U. Why U? Something from Latin. I can't remember what. And why U and not E for energy? Because E is taken up by electricity, electric field, and it's important there, and it's totally different. So I'll write a KE all the time. Let's get the energy of motion. First, I started out with the definition of work. Oh, you know what? That's force times distance. And then it says, hey, F equals ma. I guess it wants me to replace the F in this equation with, oh, let's do that. And then I'm going to get very clever. I wrote, since 2 times 1/2 equals 1, here's what I'm going to do. I am going to put a 1/2 in the front, m, and I'm going to put a 2 right there. Why'd you do that? Patience. First of all, if I times by 1/2 and times by 2, have I changed the answer at all? Have I? No, you're right. Why? Because 2 times 1/2 is 1. So I did this. I'm making it look different, but I'm not making it different. You okay with that, Manny? Yeah. Why did I do that? Because of this. Because VF squared equals VI squared plus 2AD. What can I replace that 2AD with? It seems to me I can replace it with a VF squared minus VI squared. That's the same as 2AD. Wasn't that clever? Oh, and you know what, Dustin? If VI is 0, if we start at rest, lo and behold, I end up with kinetic energy equaling a half mv squared. You guys saw that last year. There's a way to derive it. Where Ke is the kinetic energy an object has in joules, m is its mass in kilograms, v is its speed, not vector, just its speed. I don't care about direction, I don't care about velocity, just its speed, which means direction is going to be irrelevant. So no vector symbols because kinetic energy is a scalar, half mv squared. A little note, my love for nerd trivia. If you eat a jelly donut, that contains about 10 to the 6th joules. If a mosquito does a push-up, that's about 10 to the negative 13 jelly donuts. That's about 1 erg. An erg is a very small unit of energy. An erg is about 10 to the negative 7 joules. Do we need to know that? No, just nerd trivia. Turn the page. Or next page over. So we can already start to do some athletics. We can talk about sports. Golf, for example. A golfer wishes to improve his driving distance. Which would have more effect? Doubling the mass of his golf club or doubling the speed with which the club head strikes the ball? How far the ball goes. How far he hits the ball. So a golfer wants to hit the ball further. What's going to have bigger impact? Using a heavier club? Kiowa, convince me. You're right. Why? Shouldn't it be equal, Mr. Do It? You're doubling and you're doubling? Manny. Oh, Manny, give me the equation here. What is it? What is it? And what'd you say about the V? Since, come on, pen. V, how am I going to write that? Oh, you know what? I'll just write since V squared, 2V, so if you double the speed, how much more energy do you get? You say it loud and proud. This is why in the past 15 years, all of sports technology in golf, in hockey, in baseball, in any sport where you swing an object to hit something else, has gone into not making the bat or the tennis racket or the golf club heavier. They've actually made them lighter. And I realize that's a trade-off because there is still an M in the equation. But if I make that a tiny bit lighter, but I get way more club speed or way more racket speed or way more hockey stick speed, hey, that's a win. Because way more bang for your buck by increasing the velocity. This is what almost all of in the last 15 years or so, why have slap shots become harder? Why have driving distances in golf gone further? Why have tennis serves become, oh my God, holy smokes. It's the equipment, not the physical prowess of the athletes. That's helped a bit. They're, lifting weights and whatever, but they've pretty close to maxed that out. Now it's mostly equipment changes and technique changes as well.